In this video, I'm going to take the program from my previous video and make some enhancements to it. If you recall, that program was a very basic multi-threaded program where one thread was passing messages to a second thread. And I have that over in this window. I've compiled the program and I've have executed the program, and you can see the information has been placed out into the standard output. For more information about this version of the program, please view my previous video. The first enhancement I'm going to make is that in the first version, the messages that were being placed out into the pipe were all like character string types, where it was printable characters, and you could easily read the messages. But let's say that we had a situation where we needed to put non-printable characters into a pipe and or pass them between one thread and another thread. Then that's what this version is going to do. So in the main function, I have not made any changes other than I noticed after my first video that in my two calls to the pthread create, I had put a void pointer typecast in front of the null arguments for the fourth argument, and that's really not necessary. So in this version, I've cleaned up my code a little bit and I have removed those void pointers. So other than that, the main function should be the same. In the function that handles the writing of information out to the pipe, I now have 3 character arrays that contain the information that I want to pass from the one thread to the second thread. And you'll notice that pretty much I'm just writing these messages out. So in this scenario, when I is evenly divided into 7, I will put out 3 different messages, treating them as all one message. And doing the same thing with here, I'm just putting out one character array that's got 4 characters, and this one's got 11 characters. So down in the listening thread, there really isn't too much different with the way it reads the information from the pipe. It's still the same read statement. But since the information coming from the pipe now contain these non-printable characters, what I will do down in this section of code is for every single character that comes out of the pipe, I will turn each character into its 2-character hexadecimal notation. And that is accomplished using these 4 line of codes and basically creating a left and right side of the notation and putting that information into the character array, and then finally putting that character array out to the standard output like before. So let's take a look at how this version looks. Let's go ahead and compile it and then run it, and then you'll see that basically, yeah, it's different in the sense that now we have these hexadecimal values being put out to the standard output. We no longer have regular text messages. We now have basically what I'm going to call bytes of information being passed from one thread to the next. But the problem I have here is that, okay, well, where does each message end? I can't see that. And that's what we're going to do in our next enhancement. So let's come over to here. And you'll notice that in this version, there is no change to the main function. It's still the same. But the change we're making down here in the thread that puts the messages out into the pipe is that we're going to precede each message with a 3-character message length. So in this case, where we are putting a 17-character message into the pipe, we'll precede that with a space 17, and then in this case, where we're only putting 4 characters out into the pipe, we'll precede it with space 4. And likewise with the space 11 for an 11-character message. Down in the listening function, we are changing the way the read works, in that we're going to first read those 3 characters, which represent the length of the message. So in our first pass, where we placed a space 17 followed by a 17-character message, space 17 is placed into this character array, and that is then turned into an actual integer value. So message length is now 17. We will read from the pipe 17 characters, placing them into the message character array. And then we're going to do the exact same thing we did with the previous version of the code, and that is turn each character into its 2-character hexadecimal notation, and then place that out to the standard output. So let's go ahead and give that a try. I'm going to put that out here, and go ahead and run that. And what did I do wrong? Something went wrong. Let's try this one more time. I'm going to compile this. Oh, there it goes. That was really strange. I am not sure what just happened there. Let me clear my screen. Let's try this one more time. Let's compile it first. And now let's run it. There we go. So that's what it's supposed to look like. Basically, each message is treated as one thing. We now know where each message ends. So the final enhancement that I need to make is we need to synchronize the talking and listening threads, because they're sharing a resource, and that resource is the pipe. And let's take a look at what could potentially happen. This is the fourth version of my code, and the only difference between this one and the previous one is I've introduced this thing called a mutex. And so a mutex is a way of synchronizing threads that have shared resources. And what you do then, if you're going to use a mutex, is you have to initialize it. And I did add that to the main function, and that is done right here. Other than that, the rest of the main function is the same. But down here in the function that is writing the information out to the pipe, every time I want to put information into the pipe, I'm going to try to lock the mutex. And if it cannot lock the mutex, if another thread has it locked, then it will block, but it will wait. It'll suspend operation in this particular thread until the mutex is able to be locked, at which time code execution resumes. And in this case, I'm going to put out a message to the standard output, basically a visual clue to show that the talking thread has been able to lock the mutex and that it's written the information out to the pipe. So everything being written out to the pipe happens in between the locking of the mutex and the unlocking of the mutex. And the reason why we're doing that is, what would happen if in this multi-threaded environment we put the space 17 out into the pipe, and then only this first part of the message was written out to the pipe. And then because the system allowed the listening thread to get a chance to do some work, it would then say, oh, space 17 means I should see a 17-character message. But when it would go to execute the read, asking for 17 characters, if there were only 2 characters in the pipe, the read would return with just those 2 characters. It would not wait for a full 17 to be out there. As a result, our program would then go horribly wrong, because now we are expecting 17 characters. There isn't. We only get 2. Those 2 are displayed, but then that next character in the pipe that eventually gets into the pipe no longer represents the length of the next message. It's actually part of the previous message. So by locking the mutex, putting everything as it relates to that message into the pipe, and then unlocking the mutex, we ensure that the listening thread will not have an opportunity to read the full message, or it'll basically ensure that the listening thread can't basically read anything. So where that happens is down here in the listening thread. Now, you do know I did change it up just a little bit. I'm now reading only 1 character, because the problem with the mutex is it doesn't prevent us to read the pipe. It only prevents us from locking the mutex. So you can't prevent somebody from reading the pipe when there's data in the pipe. All you can do is prevent them from locking the mutex. So in this case, since I'm going to be extra cautious and make sure that there isn't any chance that maybe somehow the system only gets the first character of our message length into the pipe before getting the full message length into the pipe, I've changed this up to say, fine, let's only read the very first byte that's in the pipe. And if there's no information in the pipe, it waits just like before. But the moment something comes into the pipe, we're only going to read one character. Then we will lock the mutex. Now, if the mutex is currently locked by the talking thread, then this thread will have to wait. It will not go any further. But the moment that it can lock the mutex, then it will read the next two characters in the pipe. And because of the fact that we did this locking of the mutex up in the talking thread, we're guaranteed that we now have the rest of our message and the rest of the message length in the pipe. So we are guaranteed that when I do this, we will be able to read two more characters to complete the length of the message, and that entire message will now be in the pipe, and there would be absolutely no reason why the message length would not be in agreement with the read length. Basically, if we put 17 characters in there for the message, they're all going to be there. The rest of the code works the same way, where I convert each character of that message into its 2-character hexadecimal notation. But before we end the loop, we do unlock the mutex so that we don't block the talking thread. We want to be able to let the talking thread get some more information in there. If we didn't unlock the mutex, the system would never add any more messages to the pipe, and it would just kind of hang. So let's go ahead and run this version, and let me go ahead and put this in here like this. 2, 2, and let me run it. And so now when we run this, I had added that extra little message in here about that the talking thread locked the mutex. And you can see that sometimes because of the way threads work, the talking thread got to put a message into the pipe, then the receiving thread got a chance to lock the mutex and then retrieve that message and put it out onto the standard output, and it went back and forth and back and forth. But then every now and then the talking thread got to read or put 2 messages into the pipe, but then the listening thread got to listen or read those 2 messages. It kept them separate though. There's no merging of the messages here. And down here when I ran it, okay, in this case, the talking thread got to put 5 messages into the pipe before the system gave the listening thread a chance to do some work. So, and if we run this another time, we'll see that it doesn't always match up. See, this time it looks even a little bit more different. There's more times where many messages are being put into the pipe. Many messages are being written from the pipe. So each time you run this, the way the system allows time and to each thread will be potentially different. So what if you wanted to have a little bit more control over how much or how many messages were put into the pipe before the listening thread responded to it? If you wanted to create or kind of force the system into saying, look, every time the talker says one message, I want the talker to take a small break so that the listening thread has a chance to do something with that. We could put in a nanosleep, or like a 1 microsecond pause in the talking thread, and that's what I'm doing right down here. So I'm passing in a value of 1 microsecond, and I created or defined those up here. I basically said that a microsecond is this structured time spec of, it's actually this one here, of 0 seconds and 1,000 nanoseconds. So that's the structure of time spec, is the number of seconds and the number of nanoseconds. So if you needed to pass 1 nanosecond, it would be 0 and a 1. Whereas since a microsecond is 1,000 times larger than a nanosecond, we pass in a value of 1,000 here. And a millisecond is 1,000,000 times larger, so it's 1,000,000. So a 1 microsecond pause, though, is enough to kind of force this system to definitely do a talk one, or have the talker thread do one thing, have the listening thread do one thing, back and forth, back and forth. So let's compile this, let's run this and see what it looks like. So now you can see that, oh, actually it was not enough time. Look at here. Even though I told it to pause for a microsecond, it didn't do that. So we're going to change this to a millisecond. Millisecond. Microsecond, I thought for sure would be enough time, but it obviously was not. So let's do this again. And now it looks like the millisecond is kind of faking this out to make sure that every single one of these messages, once it's put into the pipe, take a break, talker, let the listener do something. And that now seems to be happening. So you may have to play around with this. A 1 millisecond may not be enough time. You may have to go to a slightly larger value. But just keep that in mind if you're trying to force the system to make room for one thread and not let one other thread take up too much of the time as far as putting messages into the pipe. So that concludes this video, and thank you for watching.